who's going to be talking about zooming in on star and protoplanetary disk formation. Thanks. I'll give you the 2-minute warning.
Thanks. I'm from the Center for Star and Planet Formation, which is a center of excellence that I've existed now for 4 years in Copenhagen. And the work has been done together with postdoc Truls Saugbøl and 3 students, and with Paolo Padovan in Barcelona, and with our colleagues at the Niels Bohr International Academy in Copenhagen. It's, as far as I know, a first-of-a-kind thing. It's an ab initio simulation of formation of circumstellar disks using adaptive mesh refinement to zoom in over 9 orders of magnitude in scale. We choose an outer scale of 40 parsec, similar to a GMC or a GMC fragment. And the inner scale is really determined not so much by a requirement to go close to the star, but by a requirement to resolve the vertical scale height of a very cold disk. So even 0.01 AU is marginal for resolving a disk at 1 AU if it's 10 or 100 Kelvin warm. So the ratio of the outer to inner scale is 29 orders of magnitude or 22 orders of 2. For a technical reason, we couldn't go to 30, but there's no economical problem in going to 30 because, as I will discuss, the cost depends logarithmically on the number of levels. So far, this is just a proof of concept. We've done it for 1 solar mass star out of our simulation with hundreds of star formation examples. And the plan is to get a statistically significant sample so we can both study what is the typical fate of and history of circumstellar disks and what is the range of extremes that can happen. So the basic idea is to anchor the dynamics in a well-observed spatial range. And GMCs are really well observed. We have the Larsen relations that specify essentially the velocity dispersion as a function of size and mass scales as a function of size in a well-known manner. And we know from the BN relation what the typical magnetic fields are. These are well-established facts from 30 years back. And the great advantage of this is that it avoids having to pose unknown initial and boundary conditions. And it's very similar to techniques used in cosmology or in galaxy formation, where one anchors a thing in the GMC or in the cosmic microwave background fluctuations, which are well calibrated. So the drawback is that one must cover of the order of 9 orders of magnitude in size from GMC scales to the vertical structure. However, even if one was to simulate only protoplanetary disks in isolation, having to specify totally arbitrary conditions, one would still have to cover 5 orders of magnitude. And because of the logarithmic dependence on depth, that would only be about half as expensive. So this is twice as expensive as a totally useless intermediate simulation. Having said that, I need to explain that we do it in 3 different steps. First, we run simulations for tens of millions of years on the GMC scale, and we create hundreds or even thousands of stars. The total mass in the box is about 100,000 solar masses. The cell size there has, it turned out, to be able to recover the IMF reasonably well. It needs to be about 250 AU, so about 16 levels of 2 is necessary to get a good IMF. And we need to have a good IMF because we need to know that we create solar mass stars reasonably realistically. So then we have the stellar accretion scale defined by the requirement that we need to afford about 100,000 years. That is the time roughly that it takes to accrete the mass of a solar mass star. And that in practice gives us 22 orders of refinement and a cell size of 2 AU. Then we can do time durations of about 100,000 years. Finally, we have the accretion disk scale, where the dynamic scale is about a few AU, and we have 29 orders levels of refinement, and the time duration then is only 100 to 1,000 years. So the zoom-in base, and note that in this case, we actually have all the levels up to the largest scale available in the same run. There's no real gain in removing the outer scales when doing this, because most of the cost lies in the inner scales. So when you zoom in size, you also need to zoom in time. So here's a sketch showing the 3 time scales. As I mentioned, the middle one needs to be covering about 100,000 years. And I will discuss the accretion rate profile in a brief moment. But from that accretion history, we pick out 3 different points in time. One, which is the early phase, where the protostar is only less than 1% of solar mass, just after the zinc particle has formed. And just to mention briefly then, that the magnetic field is then essentially hourglass-shaped, and it is controlling the accretion completely. So the accretion is able to essentially free fall onto the particle at the initial time. The next example is then at the mid-age, and at that point, accretion is able to create at the center a disk wind and a jet because of the angular momentum and its fight against the magnetic field. And finally, late in the evolution, when the accretion rate has dropped very much, the magnetic field is essentially in the disk plane. And now the disks are reasonably large, whereas in the meantime, the disks are really small and varying in time and orientation, actually, during the accretion event. So, why not do the whole box? Wouldn't that be simpler and would create lots of statistics? Well, if you were to run a current speed, a full simulation, it would take about 100,000 ages of the universe. Because you'd have to run 1 petaflop for 10 to 15 years, which is about 2 to the 50 times the largest supercomputer grants you can get today. However, if Moore's law applies, then we know 50 powers of 2 will take only about 80 years. So here's the first zoom part, where we go from 40 parsec to essentially protostellar core size. And we zoom in on an insignificant little filament at the back of this box, which happens to produce a solar mass star. It's the little thing there. And then we zoom in on that. I'm sorry, I must restart this previous one here because it ended before time, I think. Let's see if I can get the end part of it. Yeah, all right. So here we are. This is first the fragment dressed with a magnetic field. The local magnetic field is important in creating this filament and in anchoring this gas, which is in the protostellar core, against the background environment. And if I remove the magnetic field, this is what it looks like, and it's the thing in the center that is the protostellar core. Its size is over 10,000 AU. So the next step is then going from that down to all the way to 1 AU. I do this in steps to speed things up. This is for the middle case, where the accretion age is about 50,000 years. And here, what looked like a smooth core has quickly, because of the accretion, become very filamentary. Doesn't want to play. That's strange. What a shame. Okay, well, we'll skip to the last part of it then. I should tell you that it's just a mumble jumble, because while it collapses and while the magnetic field is strong, there are filaments and filaments and filaments and filaments all the way down to the smallest scale. So actually more interesting to look at this one, which is the final zoom from 15 to about 2 AU. So here we have a nice disk, except it has this funny mountain ridge in the background, and that is actually explained if one looks at the magnetic field. Unless the movie stops again now. So one should always play this on one's own computer, because PowerPoint on one computer is not the same as PowerPoint on another computer. The point here is that that ridge is actually carried up by a magnetic field. It's lifted up by a magnetic field, which is mostly in the plane, and I can at least now go back to the slide that has the zoom-in view here. So in the end, this is exactly the situation. And we can see the magnetic field is essentially in the plane, but it's also tilting out of the plane, and I can lift gas up or down on the plane. So one of the bottom line conclusions for observers is that nature is complicated. It's not consisting of nice disks that are completely flat. And accretion does not occur from the edge of the disk and inwards. It appears, it happens through magnetic field lines down onto the disk at a distribution of distances. Okay, well, let me try and find my slide again then. So let's look at the accretion rates. We measure the instantaneous accretion onto the central zinc particle. It peaks already after about 5 kiloyears. It rises very quickly from the initial state, and then fluctuates because of changes in field topology. After that, it decreases nicely exponentially, which is also what one finds observationally. And the reason why this happens is really, really interesting. Here is a plot showing the distribution of mass as a function of distance from the central sink. The dashed line is the initial distribution. It's very steep. But very quickly, during this transition from 0 to 5 kiloyears, it goes to a power law. And if you were to have a ruler, you could find that the slope of this power law is 3/2, which is exactly what you expect for free fall. With the velocity going as 1 over r to the minus 1/2, you'd expect exactly this mass distribution. So it shows that during most of the accretion time, the accretion is essentially free fall accretion guided by the magnetic field. And the importance of the magnetic field is really one thing you should take home from this presentation. It's important because it makes fast and efficient accretion possible. And it's important because it produces bipolar outflows. And those are a major sink of angular momentum, but also energy. Energy. I advise you to look at a paper by Zani et al. From 2007, where they show that more than 90%, perhaps 95% of the energy is carried out in the outflow. So the game comparing disk luminosity with accretion rate needs to take that into account. It's a really huge factor. Finally, a speculation, an interesting one. With so much magnetic field in the disk being essentially force-free, following the rotation around the disk, that could suppress the turbulence. And as you know, turbulence, or the argument about turbulence, is what killed the Goldreich and Ward initial theory of how you form planetesimals. So maybe we can re-enable the Goldreich and Ward thanks to the magnetic field. Briefly about disk wind and outflows. In the mid simulation here, we get a central disk jet with an outflow speed of about 100 kilometers per second because of a constrained pinched magnetic field. At the same time, there is a wider disk wind with speeds about 10 kilometers per second. So the impact of this to understand early minerals is the following. We at the center have now established that in the same parent body, you can find chondrules that differ in age by several million years. And the parent body is itself at least 4 million years old. And chondrules are really present in different parent bodies ranging from time 0. The gap that used to exist no longer exists. It was due to a measurement problem. So we have the problem of storing minerals for millions of years and then letting them accrete to the same body. I think the only way to do that is to throw it very far out with the outflow. Finally, the impact for these simulations on transport of short-lived radionuclei you can read about in a recent APJ letter from last month, showing that the transport of SLRs from supernova is rapid enough to explain the initial abundance of 26 aluminum. So to summarize all of this is a first-of-a-kind simulation going from GMC scales to a fraction of an IAU over 9 orders of magnitude. And the point is that you anchor the properties in the GMC scale, very well-known properties. It's a first proof of a concept, and the plan is to make this for a reasonable number of stars. And it already demonstrates the crucial importance of magnetic fields and of large-scale flows. Thanks for your attention. Sorry? Yeah, yes.
Okay, we've got time for some questions.
Aake, as you know, there's this debate about whether you can form in a magnetic medium, whether you can form disks at all, the so-called magnetic breaking catastrophe that's been in the literature the last few years. One resolution of that ourselves and a few other groups have now found is that turbulence may wreck up those torques and prevent them, sucking out all the angular momentum, allowing a disk to form. And I'm just wondering what you found.
Well, we can see here that
get disks. Are they Keplerian? Could you tell us some of their properties?
We can see here that during the early phases of the accretion, magnetic braking is extremely efficient and creates at the center a tumbling little disk of a few AU only. And it's only towards the end where two competing effects are taking place here. The mass of the disk is getting smaller and smaller, but at the same time, its grip on the magnetic field is getting weaker. So the magnetic field can re-expand and leave a weaker field that allows a nice disk to form. So I think these recent results have really pointed at exactly where we want to be. That the initial magnetic braking is really useful. It's helping the accretion to happen very fast. If you take a typical molecular cloud fragment and let it conserve angular momentum, its size would be about 10,000, about 1,000 IU if it had rotation velocity of 50 to 100 meters per second. That's simple back of the envelope estimate. And of course, then it would have a hell of a problem to concentrate all that mass into something at the center. But that is not a problem because of the magnetic field, and only because of the magnetic field.
Hi, Jake Simon, CU Boulder. So I'm interested in your kind of final configuration for your magnetic field once you get to the circumstellar disks phase. Do you have any robust constraints on geometry and sort of plasma beta or magnetic field strength once you get to the sort of protoplanetary disks phase?
You're asking if there is any evidence from... I couldn't quite hear the question.
Oh, I'm just wondering what the, if you can say anything about what the, when you're at the circumstellar disk phase, when you're at that scale, what the magnetic field looks like, what its strength is relative to the gas pressure.
Yes. During this violent accretion phase, there's always approximate equipartition between the magnetic field and the turbulence. So the kinetic energy, the level of kinetic energy and magnetic energy are always similar. That means that the magnetic field actually gets very strong, of the order of a Gauss or so on the scale of the whole disk, and even much more at the inner part of the disk. And this is not strange. I mean, it would be really strange if you did not have equipartition between kinetic energy and magnetic energy during this phase.
Okay, I'm afraid that's all we've got time for now. If you can join me in thanking Aake again.